But there's one topic that I want to go back and do, and that's the damped oscillation. So halfway through, or like maybe closer to the end, we had this slide here. I want you guys to come here. Talk about this topic called damped oscillations. And damped oscillations is kind of like the more realistic version of what happens in a simple harmonic motion. As you know, um, a pendulum, if I had to swing a pendulum, it wouldn't go on forever. It would eventually stop. And the reason for that is because it's in some kind of resistive environment or medium, right? So this pendulum is swinging in the air, which is kind of like creating drag. Or if it were water, it would slow down even more. If I had a hanging mat, right, so imagine like it's in honey or something versus being in air. And honey obviously is going to slow down much more quickly than if it were in just regular air. And of course, if there was no medium, so if you're in vacuum, then we're talking about oscillations that would go on forever. This is not the same as friction. Right? Friction is really a kind of energy lost to kind of like the mass itself touching against something else. We're not talking about friction, we're talking about, it's called damping. What I want to draw your attention to is this curve here. Right? And what does this curve represent? Look at this slide. You're looking at this graph. You know that you're functioning from here. What does this curve represent? What do you think? Yeah, exactly. This is the amplitude curve, right? And so this amplitude has some kind of variable function. When we looked at it before, amplitude in a regular undamped oscillating function, amplitude is always a straight line. So if the equation for amplitude on a straight line would just be A, right? Because it's independent of time. It's just that the A doesn't change, always A. But now with time, so if this were time moving forward, then amplitude changes. Right? So now we have what we call A of t, right? Or a function of the amplitude with respect to time. So let's talk a little bit about that. We have A of t, that's a t, okay? And if again, if I go back, what shape does that amplitude look like? I want you to ignore the bottom part, ignore this one here, right? And take a look at this. What kind of function does that look like? Does it, and try to imagine and describe whether it ever hits this axis, or what do you think? Tell me anything about it. Say words. Shiny. Yeah, absolutely. So this would behave like an asymptote here, this horizontal line, and therefore the amplitude would theoretically decrease forever until we can't see it anymore, until it's so close to it that it might as well be zero. So what kind of function does that? What kind of function decreases with respect to time but never actually touches zero? Inversely proportional? Yes, sure. Inversely proportional is good, but there's a way to describe that. It's exponential, negative exponent. We talked a little bit about it, Max. You know anything about that? What's that? Very, very close. Max is saying the natural log, but it's the inverse of the natural log. It's what we learned in E&M last year, what you guys might have learned in chemistry with radioactive decay. What was the principal term? 1 over x is close. It's e to the power of negative x, right? Which is basically 1 over x. They're very similar. I don't want to say that that's wrong, but in this case, the equation is 1 over, it's e to the power of negative x. And so what we have is some, maybe I should go back actually, because if I were to graph this here, it actually intersects the y-axis. So if it intersects the y-axis, I can't say that it's 1 over x, because if it was 1 over x, it would never touch the y-axis. It would go up to infinity. So it can't be 1 over x. But it's similar to that, though. It behaves like that, everything beyond 0.00001. So we have some initial value, and this initial value that intersects with this y-axis, we're going to call that the initial amplitude A naught. Okay? And so that means that this is a product of A naught. It has an initial amplitude. Kind of like when we're doing current with respect to time. Current, there was like an initial current. Do you guys remember that? Please don't forget it. Otherwise, well, we learned it from nothing. But I'm not going to hold you to it. I'm not going to test you on anything. So yeah, so there is an initial amplitude, just like before there was an initial current, or when we're talking about radioactive decay, there was an initial mass, right? And so here there is an initial amplitude, and then it decreases from there. And it decreases with some factor that's proportional to the exponent of E. I'm not going to write the rest right away, because I want to talk about a value. I'm going to add a new value into this thing. This is the value B, okay? And we can call this the viscosity of the medium. And you guys know that term viscosity? Can someone describe for me what viscosity means? Yeah, it's resistance to motion, resistance to motion. And so something like I said before, honey is very viscous. Something like vodka is very unviscous, right? Because it's got it's got weaker bonds relative to something like honey or molasses, or what else could be very viscous? Honey, molasses, what's really thick? Maple syrup? Maple syrup? What were you gonna say? Mucus? Uh, like like you're talking about like and you're sick and you just spit out your mucus. It's like kind of green. That's what we're talking about. That's more solid. So we're still talking about fluids here. Maybe maple syrup or lava, cream. There you go. That kind of stuff. Very viscous compared to um, to let's say like water, to ethanol, to any kind of the solvents that you guys might be using in organic chemistry, or you guys used in organic chemistry. Yeah. So B is going to represent that thickness of that material, and it doesn't have to necessarily be a liquid. It could also be a gas. So our air has some fluidity in it. So you can have thicker air or thinner air, and that would also be affected by it. That would be, the B would represent that thickness and thinness of the air. It's a characteristic property of any substance. And so we need to take that into account when we're talking about how this oscillation is going to dampen. So if I were to go back and say this is the oscillations in air, what would this graph look like if it was in a very thick medium? Would it die off slower or would it die off less fast? No, sorry, would it die off slower or faster? Faster. So what would it look like, the graph? It would be I'm talking about just this red part here. Would it be like a slowly stopping curve, or would it be rapidly stopping curve? Yeah, it'd be a rapidly stopping curve. So it'd look more like this. This would have say it's called this B1 and they call this B2. In this case, B2 would be greater than B1. Okay. Oops, sorry. So that means this term has to play a part into the curve of the amplitude. All right. So now I'm ready to show you the exponent factor here. So this is negative b over 2m times t. Okay? Yeah, e. Yeah, like the irrational number. Yeah, mass. M is mass in this case. Yeah. Is there ever a situation where mass is in grams? I think. Yeah, but in chemistry, do we use grams? Yeah, you do, because you use molar mass in grams and molar heat capacity in the grams. Yeah, you're right. That's confusing. So let me ask you a question here. Based on the equation we wrote, if I had to draw a same graph in the same medium with with a different mass, what would the graph look like? With a heavier mass. Would it slow down faster or not as fast? Not as fast? So what would the graph look like? Just the amplitude graph. Max? Yeah, it would be closer to, it would be less steep kind of thing, right? And then you would use those shapes to model your oscillations. And we're going to have to talk about our oscillations because the frequency is going to be changing as well. Any questions so far? Something strike you as weird on what I'm drawing right now? If I were to draw just the amplitude, what's weird about what I just drew down there? This is amplitude here. There's something inherently not correct about it. What do you think? You mean the x-axis? Right, it never touches the x-axis. In real life, it would. That's where friction comes into play. Yeah. But in so this is how damping is not the only factor that makes things slow down. Friction is also, and it's a matter of loss of energy. That's not. That's a very good observation. That's not what I was looking for. Though. This is amplitude with respect to time, right? And if we look at it here, there is an amplitude, and there's an amplitude, there's an amplitude. Does that strike you as weird what I just did there? I didn't draw the whole line. I just drew lines after, well, from here to here, from here to here, that's one period, from here to here is one period, from here to here is one period. But here, I drew a continuous line. Is that, yeah, go ahead. That's what the mistake might be, is that you might mistake this for distance with respect to time, but it's not actually distant with respect to time. This is really just the oscillations, and it's the amplitude of, so if I were to ask you, what's the amplitude at, oh, that's a bad example. Let me redraw. Even that's a bad example. Anyways, it doesn't matter. Let's say that dotted line I just drew is not on a peak, okay? And I asked you, what is the amplitude at, let's call this 1 second. I'm asking you for an amplitude, but that answer that you get is not the y value of that wave at that time. Because the y value of that wave at that time is just below the maximum that it would reach. You guys understand what I'm trying to say? Yeah, I'm finding myself, that was a bad explanation. Let me restart. And also my drawing is bad, so I'm going to redraw my drawing as well. Yeah. Okay. I redrew my graph now. At 0.1 seconds, I have a value for amplitude, right? Because this here, this function, this line here represents amplitude with respect to time. But amplitude, your wave only hits the amplitude here, 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 and so on and so forth. And here, on this dotted line, the wave doesn't actually hit the amplitude, but it still has an amplitude at that time. Okay? It's this value that you're going to get when you put in the, when you punch in your equation and you say what is the A of 0.1 second. So then you do, okay, A naught multiplied by E to the minus B over 2M multiplied by 0.1 seconds, because that's what I'm asking you about. Right? If you plug this in and you find a value for A, what you're finding is not the wave value at that time. What you're finding is the amplitude at that time, and your wave won't necessarily hit that amplitude at that exact time. That's what I'm trying to say. That make sense? So back to this slide here. So we have an equation to determine the amplitude with respect to time. Now we need an equation to determine the actual wave value. Before we do that, we need to figure out this frequency, this new frequency, because we figured out before that the frequency, let's say we're talking about a spring oscillation system, right? It's going up and down. It was k over m, right? And so this is the frequency of the oscillation, how fast it was going up and down, the angular frequency. And this is not necessarily the case anymore because you have some damping. This value is also going to change as well. So we have a corrected value now. We have a corrected value now that we're going to call angular frequency prime, right? And this is going to, you can call this the damped angular frequency. And there's a correction value here for it. It's going to be the square root of k over m, because that's still very important. But now you have to incorporate that b value in there as well, right? So it would be b squared over 4m squared. And so this is your damped angular frequency. I'm sorry? I'm not sure. Say that again. Yeah. Talking about this here? Yeah, that's mine. And now finally we can write down the full wave equation. So now we can say that your wave with respect to time is equal to its amplitude. And now amplitude changes, right? So we can't just write amplitude, we have to write the function of the amplitude times cosine of, now we have to also use a damped angular frequency times time. And you can add in phase angle in there too. So this would be the total wave equation. This would actually give you the y position of your wave. I just realized I can create one. Oh no. Okay, hold on. Any questions on this? Let's come up with an example. I'm just going to create it right now on the spot. So my apologies if the numbers don't work out perfectly. So we're going to a spring mass system, or mass spring system, an MSS, mass spring system, with a mass of, let's say, 0.5 kilograms, oscillates and damps. After how many oscillations is amplitude 1/10 of the original amplitude? In this case, spring constant, I'll make it equal to 35 newtons per meter. And the B is measured in kilograms per second. I should have told you guys that. Here it is now. It's going to be 3 kilograms per second. Can you maybe, if you want, just go back in your notes and write down the units for cubic kilograms per second. I think this works. So I'm going to read it again. Mass spring system with a 0.5 kilogram mass oscillates and damps. After how many oscillations is the amplitude 1/10 of the original oscillation, of the original amplitude? The spring constant is 35 newtons per meter, and the viscosity is 3 kilograms per second. So what would be the first thing that you would do? Find the initial amplitude? You could. What else would you try to look for? When I'm talking about how many oscillations, that's indirectly asking you about what? Period. And when I'm talking about period, you're also talking about frequency and time, all right? So we have to connect these three things together. So let's go ahead and write down our equation. We know that the amplitude with respect to time is equal to the initial amplitude times this equation. Okay. And we know that the ratio between the amplitude at however, whatever time this is, divided by the original amplitude, we know that that's 1/10, right? So that means I just brought this down over there, and I'm left with this equation here. You guys follow what I did? I can rewrite this as 0.1 now because we're dealing with math. So 0.1 is equal to that factor, that decreasing factor. So we just have to solve for t now because we have b and we have m. How do we solve for t? What's the next step algebraically? Yeah, you have to do that ln, or the natural log of both sides. So ln of 0.1, and that ln of e to the power of anything, the ln of e to the power of anything is that anything. So we're going to say that e negative b over 2m times t. So I got rid of that e now. And now it's just simple algebra to isolate t. So it's going to be 2m times the ln of 0.1 divided by negative b. Someone give me a number for that, please. Units? Second. I need one more person to confirm this. Confirm? Okay, good. All right, so that's how much time it took for that oscillation to reach that amplitude. But I'm not looking for the time. looking for how many times did this thing bob up and down before it reached there. So let's find out. What do we need to find that out? How many times it bobs up and down? I need to find the angular frequency, exactly. So let's find the frequency or angular frequency, same thing. But let's find the angular frequency first because we have an equation for that. Square root of k over m minus b squared over 4m squared. So again, plug in the values. We have all of those variables. Tell me what you guys get. 7.81. Can someone confirm? Units? Hertz? Not hertz. It's angular frequency. Radians per second. If I wanted to convert this into hertz, because that's what I need to multiply, I need to remember this equation here. 2 pi f is equal to omega, and therefore omega over 2 pi is equal to f. So now I have 7.81 rads per second divided by 2 pi. It's going to give me my frequency in hertz. What'd you guys get? 1? Just like 1.24? Okay. I'm ignoring significant figures. 1.24. Now we're talking about hertz. Let's just define this for 1 second here. So I have 1.24 cycles per 1 second. So how many cycles is that equal for 0.768 seconds? That makes sense what I did there? Okay, great. So did I even do one oscillation? I think I barely did one, eh? How much? 0.96. Units? Cycles, oscillations. All good. Okay. So I barely even made it to 1 cycle before I was able to reach an amplitude that was 1/10. So is this a value of a B value of 3 kilograms per second? Is this something that's relatively thick or relatively thin? Thick, because you reach 1/10 of your original amplitude. You already lost 90% of the amplitude in less than a second. That's pretty thick, right? Something that would be less resistive would take much, much longer for it to reach 1/10 of its amplitude. If I had to, we're talking about this mass spring system here. If we go back just one slide here, I told you that the angular frequency is k over n minus this whatever expression is. This is already very biased equation because it only works with what kind of system? Yeah, it works only because I have a k. It works only with springs. So if I had a pendulum, I would actually use this equation for the pendulum. So if I had so this would be for MSS, mass spring system. If I had a pendulum, what would it look like? Is it L divided by G or G divided by L? I can never remember actually. L divided by G? You guys sure about that? G divided by L. Minus, and now you can just use the same corrective value. E squared or 4m squared. This would be for, now it would be for a pendulum. Makes sense to you guys? Any questions on this? Because I'm done with it. So now it would be like that. Are we good to move on? No. Everything up until before this. No. So no questions? It's pretty straightforward. It really is just applying some equation and understanding that, that the oscillations will slowly die off. According to this model, does it ever stop? All right. We're good? To close this, open up PowerPoint number 4, waves on a string. Or speed of a wave on a string is what it's called. All right. So the title of this is very telling because we're talking about string. There you go. The title of this is very telling because it's really talking about waves on a string. Okay? So don't think about sound yet. Don't think about pendulums or springs. We're kind of moving away from springs and pendulums right now, and we're going to head towards the more abstract stuff of like sound and light. But we're not even there yet. Okay, we're talking about string, and we're talking about string is still a physical thing that has velocity that we can measure, right? And you know, we can see the wave happening. In sound, we don't see the wave. In light, I guess you can say we see it, but we don't see the wave part of light. So we're going to talk about standing waves and all these things. We'll get to it. But there's one thing that's very important is that we know how to measure the speed of a wave. Do you guys remember what the two factors were to determine how fast the wave travels in a string? There was two variables. Go back and look at the YouTube. Think about, yeah. Yeah, and what was the other thing, Max? Frequency. You're talking about this equation, wave velocity is equal to frequency times wavelength, that one? Yeah, that's for all waves. But I'm talking about specifically for waves on a string. So like tension and mass length density, all right? And the symbol we had for that, do I have it written here? I don't have it written here, let's write it down. The symbol for that was mu, if you remember. So the velocity on a wave on a string, so wave string, is equal to the tension force divided by this coefficient. Okay, and this was the mass length density. Mass length density. What was the example that we used? Violin, yeah. Guitar, okay. String instrument. This whole part, think of string instrument. Okay. All right. So, okay, so here we have the wave that the speed that a wave travels on a string, it depends on its tension and depends on its mass length. So if we're talking about guitars again, because we're gonna get into the math of this really quickly. If we're talking about a guitar string, how hard I strike it, is that going to change the notes that I play? It's not going to change much, in fact. It might change the amplitude, but it won't change the sound that comes out of it. The speed of it's not going to change. This idea is very important that that waves travel at different speeds in different mediums. We kind of talked about that with the damped oscillation, but that was really of a dying out. Let's say you had like a speaker playing sound in water, it would actually travel at a different speed. It would sound differently than if you had that same speaker outside of water. You guys heard of these guys on YouTube called Slow-Mo guys? Yeah. They did this one experiment where, by the way, these guys are not scientists. They're just like really dumb people with a lot of money. And basically what they do is they pretend to be scientists and film things in super high speed. So they bought this camera that can measure things at an incredible frame rate, right? So they can slow things down a lot. Like we're talking about like hundreds of thousands of frames per second. So imagine someone getting slapped like that and then watching the skin just go boom. It's fascinating, but it's kind of mindless. But in any case, they had this one experiment where someone had asked them, it's kind of like a Mythbuster type of experiment that they were doing is, where are you the most safe from a grenade? So if someone tosses a grenade, is it better to jump in the water or stay on land or duck or whatever? And so they did all these experiments. And what they had was, it was pretty cool what they did. Again, don't try this at home, because these guys are pretty silly. So they had a swimming pool like this, right? And then here they had balloons attached to the bottom of the swimming pool. And there's water. And then there were balloons that would float in here. Okay? And then they had a grenade here. So I asked me why I'm super a drawing grenade. Just because I'm Middle Eastern doesn't mean I like grenades. All right. So they ignited a grenade here, they ignited a grenade here. And what you can clearly see, like super visibly clear, is that this thing here, this grenade that detonated at the exact same time, this one here reached all the way here before this one could even reach the first balloon, right? And the reason for that is because waves travel so much faster in water than they do in air. And it works the same way with sound. And you've heard of echolocation. We talked a little bit about it. No, we didn't. You might have talked a little bit about it in mechanics or in high school when you guys did optics and waves. Did you guys learn about Doppler effects in high school? You might have maybe listened to it. You learned a little bit about it there. The dolphins who are talking through echolocation, one of the reasons why it works so well for them is because they're making these squeaking noises underwater, and the sound travels fast, so they can actually react to the sound that they're getting much more quickly than if it were in air. All that to say that waves travel a lot faster in water than they do in air, and not only that, just in different mediums, right? So if you're going to make a general statement, is that the wave speed depends on the medium that it's in. Right? We're not considering that this wave is going to go this direction and then out of the water. We're not talking about that. We're talking about waves that are staying in that same medium. Okay? All right. So we have this idea that waves, the sound travels faster in water than through air, and depending on the medium. So you can even make the conclusion, you can make the generalization that sound actually travels faster in any medium that's denser. All right. So for example, if I were to say, what's faster, the sound of the speed of sound in water versus the speed of sound in concrete, we would say the speed of sound in concrete because it's a more dense material. Okay, so sound travels faster in denser material. By the way, you can spend hours watching these guys' videos on YouTube. They're very fascinating. But again, they're don't expect a lot of science out of it. It's just fascinating to watch. You know when you see like someone take a really sharp knife and cut a perfectly piece of jello or something, and then it's got like satisfying that smooth motion. Like all their videos are like that. Okay, so back to it being on a string. We know that if I were to disrupt, I'm going to skip all this actually because we're going to do something. We're going to come back to all this and it'll all make sense. But we're going to do a online experiment. Here's that equation that we talked about before, the speed of the wave in a string, right? So it's a tension force. It's proportional to the tension force, or square root of the tension force over the mass length density. Skipping through all this because I want to show you one thing. I want to show you this. How much time do we have? It's 2:30. Oh, that's actually, I'm going to ask you guys to do it. Go on Moodle and download the lab called Virtual Lab string something. Okay. Play with it for 30 minutes. Do what it says on it. Try to do the little activities. It shouldn't take long. And then we'll come back and we'll do it as a class and we'll derive some expressions. It'll make a lot of sense if you guys do that first. So go ahead, play with that. Let's say half an hour. All right. So here I'm going to do is I'm just going to do one up and down motion. It says here, move the wrench up and then back down to its original position and do this motion relatively slowly and tell me what you see. So I have this. All right. What did you guys notice happen there? Yeah. So we have a wave that has a defined defined direction, right? It's going towards the right. There is no ambiguity there. Does it ever come back or anything like that? No. Was it above or below the equilibrium line? It was above, right? So pretty straightforward. It went above, and it goes on until, well, seemingly forever because it's an open window and we don't know what's outside the open window. If I had to do this downwards, what's the difference? What's the difference? Yeah, below the equilibrium line. And if I go up and down and then back up, then I have both. Okay, I have above the equilibrium line, below the equilibrium line, and it travels towards the right. Perfect. If I do this fast, what's going to be the difference? Like, so this is my slow version. What happens? What do you think is going to be different if I do it fast? If I went up and down? Smaller wave? What else? Yeah, so the wave might be compressed. Is it going to travel faster or slower? You shake your head no, but what does that mean? Nothing's going to happen? It's not going to change. Okay, so let's try to make that observation. I'm going to do a slow one and a fast one. Was the distance between them always the same? Did one wave catch up to the next wave? So let me try that again. Slow wave, fast wave. So the wave never caught up to the other one, which means that how fast I jerked it didn't affect the wave propagation speed. So it went from left to right in the same amount of time. All right. That's because we know what actually affects the propagation speed, don't we? We said that on a string, it has to do with tension and it has to do with its mass length density. I can't change mass length density here, but I can change the tension. So if I decrease the tension, let's see what happens. Look at that. And now if I increase the tension, oh, and then it becomes fast. All right, so tension does make the wave go faster. All right, so we've done this. Let's go on to activity. No, I'm going to stay with activity. No, we're going to go to activity 2. I'm going to change this to oscillate now, not oscillate, sorry, pulse. And pulse means that it's going to do one perfect wave, but just only one. Okay, I'm going to set the amplitude in the middle somewhere. Pulse width, we'll figure that out. And then tension, we're going to go back to the middle. Okay. What happens to the wave as I make a wave? It goes on, and then does it ever come back? You guys said no. It basically, the energy is lost out of the system and it doesn't come back. That's like playing the horn. All right. If you play the horn, you're creating waves inside the mouthpiece, and it's going out and it goes on forever. You lose the wave, it's gone. Okay. But now let's say I change it to a fixed end. All right. So now has no choice but to remain fixed. The wave can't go on beyond this point because this point is not allowed to move. Right? And that's really, really important. And let's try to see how that wave behaves. So we send one pulse, the wave hits it, and what do you guys notice? It comes back. That's the first thing to notice. And second thing to notice, it's now below the equilibrium line. Okay, so that's important. Write that down. Okay, so waves, when it's sending a wave to a fixed end, you're going to reflect it, and it's going to come back, and it's going to come back to you inverted. Okay, so it's reflected, inverted. All right, let's try the same thing, but now with a loose end, all right? Not an open end, a loose end. So the energy still has to stay within the system because it has no way of escaping. And let's see what happens. So what happened? What was different? Yeah, it's reflected but not inverted. Now that's important as well. Write that down. I'm not going to test how tension affects this, but if I had to ask you, how does tension affect my wave? You guys would say, yeah, the propagation will be faster or slower depending on the tension. Okay, so you guys get that. Let's talk about this thing called pulse width. This is the amount of time it takes for this little pulse generator to go up and down. So right now it takes 0.6 seconds to go up and down. What do you think is going to happen if I make it 0.3 seconds to go up and down? What do you think is going to be the difference? What's going to be different on my wave? It's going to be narrower, shorter. Okay, let's test it out. So here it is. I'm going to, yeah, let's do it like this. Whoops, I didn't mean to do two. I meant to do one. Okay, so there's that. In fact, let's try to do. I'm going to try to measure the. I'm going to make it in slow motion, so we can do this. Take time. All right, so the wave is about that big. Okay. Can I? I knew that. All right, and if I were to make the pulse length longer, so again, now that I have my wavelength is about that big. All right, now if I increase it to about 0.7, so I more than doubled it, and I'm going to restart, and I'm going to send a new pulse. And take it off slow motion, I suppose. Pause it like that. All right, you can see my wavelength is now increasing. Okay. All right. Now, here's the more important part. Okay. Everyone needs to pay attention to this because this is very important to building what's coming up on the next few slides. If I set this at a fixed length, fixed end, and I send a pulse, and I'm going to do that thing that I I challenged you guys with originally to get it so that this green one doesn't move. So let's try it together. I'm going to put it in slow motion so I can make sure I do this correctly. I'll put this in the middle. Maybe I'm going to do this real quick. All right, I'm just going to pause it just for now. I want to mention to you that the amplitude is about that. Okay, that's going to be important. Maybe not right away, but it's going to eventually be important. So I'm going to press play, and I'm going to try to send a wave as soon as that one reaches the end. All right, let's see if I did it correctly. Not bad. All right. So what do you notice? What do you think is happening? What's happening right there? Why isn't that one moving? Absolutely, right? So I have a positive wave and a negative wave coming in this direction. And once they're overlapping, well, if they're equal at that exact moment, then at that exact moment, their net wave is zero, right? And so they cancel each other out. Now, is this wave, what's happening to it? This is now becoming a what? What do we call this? What do we call this again? So that's another fixed end. And look, the wave is actually bouncing off of that fixed end and coming back. And this one is also bouncing off of that fixed end and coming back. If it's a fixed end, it comes back inverted, right? And that's exactly what's happening. Wave is coming from on the top, hits a fixed end, reflects downwards. You understand? I'm going to do the exact same thing with the loose ends now, and you guys tell me what's happening. So I'm going to start it as soon as my wave reaches the right. I'm going to send another wave right now. All right, that is not a good one, but it doesn't matter. What did you notice? Let me restart that. I want you to tell me what happens when the two waves meet. All right, so the waves are coming in. When the two waves collide, tell me what you notice. Still not good, but anyway, it doesn't matter. What's going to happen in the middle? What happened? Higher amplitude. What do you think happened to the waves? They added up. That's the important part. Okay, let me pause this. So they're about to come down again, and they're going to add up. And boom, it went all the way until there, whereas the amplitude is normally just this. And that's exactly double the amplitude. In fact, you can say that these two amplitudes, they added each other up. And so in the last example, the waves canceled each other out. In this example, the waves added off each other. These two terms are very important. You're going to write this down right now. It's called constructive interference when they add up, and destructive interference when they cancel each other out. I can write them on the board. Constructive interference and destructive interference. Okay? So that makes sense. Constructive, you add them on top of each other, you're constructing, and you're destructing when you cancel each other, cancel them out, and you subtract the weight. All right. When I had my destructive interference at this point, it was just one wave that was canceling each other out each time at this point. What if I sent two waves and two waves coming in this direction and they canceled each other out on these two? Or even better, what if we had continuous waves coming from both ends further at another point. And here's what I mean by that. I won't be able to get it working all the time, but you'll see it's in action for at least a few seconds. So let me try this. I'm gonna take it off of slow motion. So you guys got it at about 1.45 or something like that. You guys got it for a few seconds. Is that it? 1.45. Start. Look at my right. Right. You can see that these green. Really not clear. I might better to do the slow motion. Maybe bring this down a bit. Maybe just for now, I want you to know that every single marble reaches the max and the min. Right? When this wave is going in this way, all marbles go up and down. When you're hitting that point where I told you, it's not going to be the case. Hopefully I get it right now. All right, let's just say I stop it right now. Okay? The points that are here are actually not moving a lot. All right, when I unpause it, it's not going to stay long. It's not going to stay there for a long time. So I want you to pay attention to it. The points here are not going to be moving a lot. They'll be moving very little. Definitely not the whole amplitude. And the points in between them, so this point here, it's going to go above its own amplitude and below its own minimum amplitude. And it's going to switch back and forth. And here's the most important part. It's not going to look like the wave is going left or right. It's going to be looking like it's that standing wave. That's the name that we give this kind of wave. Because the wave doesn't look like it's moving left and right anymore. It looks like it's just standing, flip-flopping up and down, okay? So I'll restart it and try to look for that moment where that happens, okay? You can see the wave is now clearly has a direction, clearly moving towards the right. And at a certain point, it's going to look exactly like the wave is not moving. Right? So here, you can still see that there's some kind of movement. Look at that green dot, not moving all that much. Look at that one, moving a lot. And now look, the wave doesn't look like it's moving at all. It looks like it's just going up and down. You guys see that? All right? Now it's out of phase again. But the point is that you can calculate a frequency so that the wave coming from this end and the wave coming from this end always cancel each other out at certain spots and add up onto each other at different spots. So you have constructive interference here and destructive interference there. Right? I mean, if it was perfect. Okay, I'm going to stop this. And I want to show you some videos. Oh, no, they weren't here. They were on your handout. They're at the bottom of this. So the speakers in the classroom don't work. You guys are going to have to hear them from my crappy speakers.
So what we have here is a frequency generator. It's connected to what's called a wave driver. It's just a speaker. It's going to pump up and down at whatever frequency I set this guy to. When this guy pumps up and down, well, he sends a wave. He sends a wave down to this end, the wave reflects, comes back. Now, if I set it to just any old frequency, let me just turn this on.
While he's doing that, remember I was trying to see like what frequency it takes to get that? This phenomenon of a standing wave doesn't just occur at any frequency. There are special frequencies that you need to oscillate the string in order to reach that point of a standing wave. So here, he's
old frequency. Let me just turn this on. Well, yeah, let's go a little higher. So it's sending waves back and forth, but these waves are out of sync, if you like. They're not exhibiting consistently constructive or destructive interference at any one point. But if I set it here, for example, I have what's called a standing wave. That is, the wave that's sent down and reflects constructively interferes with the next wave that comes down right at this point. Now the waves that come down and reflect, destructively interfere with the incoming waves right here. And that's called a node. I can touch it and it still is working. So the node is not moving. Here it's moving up and down, and here it's moving up and down. And we'll see that in a second with the high-speed camera.
There is a point at which there is very little movement or no movement. We call that point.
So here we have what's called the second harmonic. It's the second possibility for a standing wave for a string that's held at both ends. Because notice this is a node, and the middle's a node. So we have 3 nodes for this wave. Now, like I said, second harmonic, well, what's the first one? The first one will be half this number, so 8.5. And there we go. It's basically the scenario of a jump rope. Now,
when there's maximum movement, it's called an antinode. When it's no movement, it's called a node.
I can find all of the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, or the second possibility. Well, if I go 3 times this number, I should get the third harmonic. Well, 3 times 8.5, I guess that was around 25.5. And there we go. So that's the third harmonic. How many wavelengths is this? Well, it's 1.5. 1.5 wavelengths. And it's easier to see.
If I wanted to get one node on either end, the no node in the middle was 8.5. If I want to divide that into 3, I had to do 3 times faster of that exact frequency. Okay, so that's going to be important for later. And now he's going to double it again. So if he doubles the frequency from what it is right now, what do you expect to see? 6 kind of bumps, all right? And that's, I'll just fast forward it a bit. He's doing it in slow motion camera. See, he's
50. And there we go. That's the 6th harmonic.
Let me show you just a couple other videos. They're really cool. That was the most boring one. So here's a wave tank. So have you guys ever been to like Super Aquafy where they have like a wave pool? This is kind of like a wave pool, but it's one designed for physics. One wave is coming from one end and the other wave is coming from the other, and we add up the amplitude, right? This is a wave coming from one end and the other end. So the amplitude in the middle is going to be 2 times that amount. What if you add a seemingly infinite number of waves into one spot? What do you think might happen? What would the amplitude be? Very odd. So let's try to see that in action. So in order to do that, physicists were like, well, how can we create a tank that has an infinite number of waves? Well, the answer to that is a circle. And so they constructed a circular loop in which all the waves are being sent. So right now, we just put this down. I can fast forward it a little bit. This graph is essentially this whole thing is going to have a lot of waves. You can even predict when it's going to happen based on like area of water. It's not only important in water, and I'm only showing you examples of water, but this next example is actually really, really, really important to consider as a civil engineer. Okay? So I apologize for how old this video is. It's from the 40s, because that's when it
As you can see, this bridge was exceptionally long and narrow, over half a mile long, only 39 feet wide. It lasted just 4 months. During construction, we see the steel girders, 8 feet tall, which were supposed to stiffen the bridge against bending. However, some up and down vibration was observed during the entire useful life of the bridge. Here's opening day. On November 7th, the bridge suddenly went into a twisting motion. The wind speed was a steady 42 miles per hour. This was enough to keep the bridge oscillating in one of its natural modes of vibration with a period of 5 seconds. A professor of engineering went out to see what had happened. He's coming back, walking with some difficulty along the nodal line, which is the center stripe of the roadway. It's remarkable that the girders were this flexible. This is photographed at normal speed. However, a collapse was inevitable after a little more than an hour of this. The car had been abandoned earlier. No one was injured in the whole affair. However, a small dog in the car was frightened and was afraid to come out, and he perished along with the bridge.
Standing waves is actually especially for the property that add up. So what happened is the engineers were okay with the 1A level of motion, right? So regular level of motion, they accounted for that. And then with these two bridges, they didn't account for when you hit the resonating frequency that you're going to be hitting double that amplitude. So there's a big motion of flexibility that needs to be accounted for. So now bridges are constructed so that their oscillations are so minimal that the tension on the cables or on the pillars are not really affected by it. But if you've ever stood in a bridge where like it's seemingly stable, but then like the cars start flowing on it, and then it starts seeming like it's moving a little bit more, that's because you're getting closer to this frequency called a resonance frequency. And you're getting close to this amplitude. But these amounts of amplitude that you'll feel are very, very safe. Like you don't have to worry about it unless you're on the circuit, and that's the suicide mission. But like that amount of vibration is actually quite normal, right? So now don't be scared. Just understand that you're hitting the resonance frequency of the bridge. There's cars driving on it. There's another bridge that collapsed because there was a marching band on it. And the marching band was drumming to the resonating frequency of the bridge. Accidental, purely accidental. And then the bridge started to oscillate in its resonant frequency. Let's take a 5-minute break. Come back. Come back at 2:50, okay? 2:55. My clock says 2:45. What is it? Is it 2:45 or what? What time is it right now? Okay, so come back at 2:50. I have this table here. It's for those of you who play guitar. And of course, because you're taking this class, you need to understand it. You don't need to memorize it for sure, but you need to understand it. Right here. So here is the 6 strings on a guitar instrument, and the tension that you need to have for each one. And if you have the tension right, and you use the right string. So here you have your really thin string because it's got a very low mass length density, and here you have very high mass length density. If you have the right strings and you put them at the right tension, and this is what you're doing when you're tuning your guitar, when you're turning the knob on the top, then you're going to get speeds, you're going to get varying speeds in the string, and that's going to be able to play the note that you want it to play. Now, why does a velocity matter, and how does that translate to sound? That's what we're going to try to do right now. Okay. So if we move on here, we're going to talk about standing waves real quick. I'm just characterizing them again. There's a couple definitions I want you guys to know. The first one being this idea of an incident wave and a reflected wave. All right. So if you remember in the example, there was a wave going towards the right. It hit a point that was fixed, and then it hit that, and then it came back, and that wave that was coming back was, what was the characteristic again of the wave coming back? It was inverted or not inverted? It was inverted and it was coming in the other direction. That wave coming back, that's called a reflected wave, all right? So we have the incident wave going in this direction, And coming in the backwards direction, we have this reflected wave. All right. And if you have them at the exact right phase, that in such a way that you've created now something called a standing wave, you're going to have this point in the middle called a node, right? And you're going to have this point here, this line here, which is going to be a lot of movement, and that's called an antinode. All right? I'm going to be using these terms quite a bit, and you kind of try to get used to it. One thing I will ask you, however, from this diagram, if I held the string here, if I held the string here, and I created this thing called a standing wave, right? I have a node in the middle, and that node is characterized by a point in the string where there is no motion. Where else on my string is there a point where there is no motion at all? Yeah, exactly. Right here and right here. So in fact, I don't have just one node in this particular example. The side nodes also count as nodes. So node, node. Okay. Make sure you define those correctly with nodes as well. So far, so good? All right. So here we are. I have my string attached to both ends. I'm forcing both ends to be a node. And now I'm going to oscillate this. I'm going to disturb this line of string. I'm going to disturb it with some frequency. All right. And remember, I need to oscillate it at a very special frequency if I want to create a standing wave. I can't just do any frequency. So I'm going to oscillate this at a special frequency, and I'm going to create one standing wave where there is no nodes in the middle, and then one node in the middle and two nodes, and we'll learn how to calculate those. Okay? By the way, I put this link here because this website, Physics Classroom, is actually really good for supplemental problems, for explanations. Their material is quite reliable. And I would definitely encourage you to go with it. All right. So here I have very many situations. And each one of these has a different number of nodes. Let's just count them real quick here. So I'm going to write the nodes here. How many does this first one have? 2. The next one? 3. And then this one? And then 5. Okay, perfect. And what I want you guys to notice here as well is that this string has a length. That length is determined by this letter big L here at the bottom, right? And that string, for all intents and purposes, is not variable. And of course, there's going to be a certain amount of stretch to it, and you guys are going to say that, well, when you oscillate it, the tension is changing. But we're going to assume that the length doesn't change and that the tension doesn't change when the length is changing. You get what I'm saying? Okay, we're going to ignore that. All right, so I want you to look at that first shape here. Actually, you know what? Even simpler. Let's go to the second shape. What does that shape look like? Let's look at the blue of the second harmonic of the second line there. That blue line, what does that look like? Yeah, a sine function, a full wave, right? That's what a full wave would look like. So here we can say that the wavelength, right, is equal to L. So wavelength here is equal to L. You can fit an entire length of a wave inside of the length of that string. So far, so good? What about the first one now? Let's go back. How many waves fit inside L? Half of one wave fits inside L. So one whole wave would be how long? 2L, exactly. So my wavelength here is 2L. All right, I'm going back to my second one now because I didn't write it correctly. I wrote L, but that's not really the truth. The truth is that it's 2L, it's 2L over 2. Okay? It's just an easier way to write it. And then this first one, I'm going to write 2L over 1. I think you know now what I'm getting at. Right? How many waves fit into the third one? Well, there's 1.5 waves, and so therefore the wavelength is 2/3 of the length. right? So 2/3 of this distance, right, from left to right, 2/3 of that distance is considered to be a wave in this third example here. So I'm going to say the wavelength is equal to 2L over 3. Can you guess what the next one is without actually solving it? What? 2L over 4. It's a physics lab up here. No, it's Tanya's office up there, no? One on. All right, well, that's great for the fourth multiple. What about for the nth multiple? What's the wavelength of the nth multiple? Yeah, 2L over n, right? So when n is equal to n, the wavelength is going to be equal to 2L over n. Okay? So far, so good? Not very complicated, right? All right. I want to write down a few things first, right? I found out that the wavelength of the, we're going to call this the fundamental frequency, this first one at the top, right? That's the fundamental frequency, the fundamental wave, because it's the first one, right? We're going to define that first wavelength as 2L over 1, or just 2L. Okay? And if I wanted to find the frequency, or let's go through velocity first, we know that frequency of the first wave is equal to, sorry, the velocity of the wave is equal to the frequency of the first wave multiplied by the wavelength of the first wave, all right? And V doesn't change. Remember, V is only dependent on tension and on mass length density. So it does not depend on the frequency or the lambda in this case. All right, so that means that if I isolate for F1, I can say that F1 is equal to V over lambda 1, right? And that we know that lambda 1 is 2L, so we can say that F1 is equal to V over 2L. That's very important. And so this F1, we're going to call this the fundamental frequency. And that's also known as a first harmonic. So far, so good? All right. That's fine. That only works for the first one. Let's try to find it for all of them. Let's try to find it for the, let's try to find the frequency of the nth harmonic. So we know that lambda n is equal to 2L over n. You guys came up with that. I'm going to derive the rest of the equation the same way as I did for this one. We said that velocity is equal to the frequency of the nth harmonic multiplied by the wavelength of the nth harmonic. And so therefore, the frequency of the nth harmonic is equal to the velocity divided by the wavelength of the nth harmonic, right? And now I'm replacing my nth harmonic with this expression here. So it's going to be the frequency of the nth harmonic is equal to velocity over 2L over n. So it's going to be the velocity multiplied by n over 2L. Okay? I went a bit fast there, so did I lose anyone? What is this expression here? We just derived it. Yeah, all right. Yeah, it's the frequency of it's the fundamental frequency. So in fact, I can even rewrite this as f, the frequency of the nth harmonic is equal to n multiplied by the fundamental frequency. Okay. So that means that if I want to get any one of these special standing waves, right? If I want to get any one of these special waves, the frequency that I have to vibrate is an integer multiple of the fundamental frequency. So I have to figure out what the fundamental frequency is, right, based on tension and mass length, and use that and multiply it by any integer. If I want to find the second harmonic, I would go multiply it by 2. And if I oscillate this string at that fundamental frequency times 2, then I would get this shape. If I if let's say I said that this was, the fundamental frequency was 12 hertz, right? What frequency would I need to oscillate my string in order to get this shape? 36 hertz, so I need whatever that fundamental frequency was, multiplied by 3 to get there. Okay? So far, so good? What's this here? This part of my wave? Antinode. And so let's count the antinodes. So here we said there are 2 nodes. How many antinodes are there? 1. Here there's 3 nodes. How many antinodes? 2. Okay, so you can figure out a way of determining or predicting the number of nodes and antinodes without having to. If I told you for the 27th harmonic, how many nodes and antinodes are there, you should be able to kind of do the math without actually having to draw a 27th harmonic wave. Okay? Any questions on that? Because the next step is going to be tough for you guys. I'm going to ask you guys to do it on your own. All right, let's go to it. We came to this conclusion. This is what the wavelength is. And I'm just reminding you that velocity is constant. Right? And that the frequency and the wavelength will compensate in order to maintain that constant velocity. Okay? All right. So here's the difficult part. What we just did was for a system with 2 nodes at either end. Right? And a node forces, 2 closed ends. 2 closed ends means I'm forcing a node on both ends of my string. And it's not necessarily the case, because sometimes I can have a fixed end on one end, right, and an open end on the other, or a loose end on the other. And the difference is that I'm going to have a node on the closed end, and I'm going to have an antinode on the open end, right? Alternatively, I can have open ends on both ends in the wave of whatever this thing is that's having an oscillation. So here I would have an antinode, forcing an antinode on either end. Okay? Here's what I want you guys to do then. Big disclaimer, I want you, if you're having trouble with this, start with this one because it's way easier. All right? If you think you're a pro, go straight for this one and then do that one. It'll take you 2 seconds to do that one. What I want you to do is derive the expression for frequency for the nth wave for both of these. Okay? So you guys have 20 minutes to do it. Go take 20 minutes to do it. We'll talk about it next class, what the answers are and what the implications are. Okay? So tomorrow. All right, so I'm going to repeat what I want you guys to do. I want you to derive an expression for frequency of the nth number of the nth wave. And I want you to derive the frequency of the nth wave for this one as well. Okay? The other class, I think 3 out of 4 groups did it. So you guys can easily do it. Have faith. Okay? Work together. You won't be able to solve it if you're alone. It really is teamwork.